Okay, so today we're going to talk about bisectors of triangles. So these bisectors that we'll talk about, you guys have already seen before, but we're going to look at a few more properties with them and also how they work when we draw them in triangles. So the first bisector we'll look at is a perpendicular bisector. So perpendicular bisector, you guys already know what that is. It's a segment, line, or plane, could also be a ray, that intersects a segment at its midpoint and is perpendicular to the segment. So you'll always know it's a perpendicular bisector with these two things, and they'll show those. If this is my segment, let's say it's AB, we'll know it's the midpoint if they make those congruent marks, and we know it's perpendicular if they make that little right angle box. So those would be our perpendicular bisectors. And there's two theorems that come with that, or really just one, and then the converse of that theorem. So the perpendicular bisector theorem just says, and I'll leave this up here for a little bit, but always remember, if you guys don't have time to write down these theorems, that this came from your book, so you can always write that down too. But a perpendicular bisector theorem, a point, or if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So what that means, if we have a segment right here, so let's say we have segment AB, and we have a perpendicular bisector, CD, which I know because it has those dashes right there showing that that's congruent, so D is our midpoint, and it's hitting it perpendicular. So if CD is the perpendicular bisector, then any point along CD will be equidistant from endpoint A and endpoint B, or those would be the same. Those would be congruent to each other. Okay, so any point on that perpendicular bisector would be equidistant from the endpoints of the segment that it's bisecting. And then the converse of that theorem just says that if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector. So if you had just drawn, if they didn't have these markings right here that showed it was perpendicular bisector, if all you knew was that you had a line here, a segment, and that these two distances from the point to those endpoints were the same, if that's all you knew, then you would also know that that point E is on the perpendicular bisector. Okay, so I'll give you a few more seconds with those, and then we'll look at a few different problems that you'll see. Okay, so I'm going to go ahead, like I said, move on, but if you're not done writing those things down, you can always check in the book and finish that up. Okay, so for A right here, we are looking for the distance BC. The few things that you can tell is that we have segment AB right here, and segment AB is being bisected, and that's perpendicular because of that right angle. So we know that C is on the perpendicular bisector, which means it's going to be equidistant from each endpoint. So if AC is 8.5, BC will also be 8.5. Okay, and for XY, and this is using just the perpendicular bisector theorem. For XY right here, this time what we know, we don't know that WY is a perpendicular bisector. There's nothing that says that Y is bisecting. What we do know is that from W to X, that distance is the same as WZ. So we have a point, and it's equidistant from both endpoints of a segment. So that means W is on the perpendicular bisector. So that YZ will be the same distance as XY, which would be 6. And this is using the converse of the perpendicular bisector theorem. And this last one down here, it's the same concept. It's just using more algebraic reasoning. We have a perpendicular bisector. Okay, I see those tick marks. Also have that right angle. So SQ is the perpendicular bisector of PR, which means the distance from Q to P is going to be the same as the distance from Q to R. And so we can just set those expressions equal to each other and then solve through for x. So we get 2x equals 4, so x equals 2. And then it wants to find PQ, so make sure, and same thing in your homework, always be looking at what it's asking for. So we're looking for PQ, just plug that x back in, and we get PQ is 7. Okay. All right, and we're also going to look at different centers throughout today and tomorrow when you draw these certain bisectors in a triangle. So if I were to draw, and you guys did this on your construction project if you remember, but when you draw the 3 perpendicular bisectors for a triangle, so you're drawing the perpendicular bisector for each side. So for AB, we have DP right here is the perpendicular bisector, EP is the perpendicular bisector for AC, and PF is the perpendicular bisector for BC. So when we draw all 3 of those perpendicular bisectors, they're all going to intersect at one point, which here is point P. We call that point the circumcenter. And the circumcenter is going to be equidistant from the vertices of the triangle. And that makes sense because if you think about, if you just look at, for instance, this perpendicular bisector right here. Okay, DP, we know any point on DP is going to be equidistant from the endpoints. So I know that P is going to be the same distance to B as it is to A. And same thing with P, since it's on the perpendicular bisector for AC, it's going to be the same distance to A as it is to C. So you can see these distances, I'm going to have to put 4 there, are the same. And that's your circumcenter. You're going to learn 4 different centers, so that one's going to be really good to write down and keep in mind what's intersecting to form the circumcenter, and it is the perpendicular bisectors. And when that happens, when you have perpendicular bisectors, they intersect at the circumcenter, which is going to be the same distance to each vertex. Okay? So this is actually used a whole lot, especially when you're talking about like triangulation and finding locations for different things and the most economic location. So Thanksgiving's coming up, obviously. So it's Thanksgiving. You and your 2 family members, so we'll call, let's see, this is you. We'll call this person, this is Weird Uncle Bob. Hopefully none of you have an Uncle Bob. So you got your weird Uncle Bob and maybe annoying little brother. Mine's Brett, so we'll just call him Brett. All right, so you got your 3 family members, and they all want access to the sweet potatoes because obviously, as we all know, sweet potatoes are the best at Thanksgiving. So where should you place them? So keep in mind this idea right here about the circumcenter. I have 3 people, which you could also say are 3 different vertices of a triangle. So I'm going to go ahead and draw out, let's see, a triangle that would connect each of these. It's not going to be the best, but so there's our triangle right here, just like we have up here. Now, if I want these sweet potatoes to be the same distance from everybody, then I need to find that circumcenter, because the circumcenter is equidistant from all of the vertices. Okay, so the way that we can find our circumcenter, find your perpendicular bisector of each of these segments. Now, I'm just going to eyeball it, but but that's definitely not it. There we go. So let's say the perpendicular bisector of this probably right about here. Okay. And perpendicular bisector of this is probably there-ish. You can already see where they're intersecting, but we can go ahead and draw this last one out just to make sure. And our last one, so mine's going to miss it by a little bit since I'm eyeballing it. But so your circumcenter is going to be about right here. Now something to keep in mind, your circumcenter may not always be inside the triangle, and we'll look closer at that on Monday. But just don't worry if you draw the circumcenter and it's not there inside the middle. It's not necessarily going to be there. Kind of all depends on what angles you have for your triangle. But there's our circumcenter. So this point right here is going to be the same distance to you as it is to weird Uncle Bob, as it is to your annoying little brother Brett. Okay, so if we put our sweet potatoes right here, everybody's got fair access. Okay, so that's one thing that's used quite a lot, especially to locate a point, is that circumcenter. Okay, so next up, those were our perpendicular bisectors and circumcenters. The next bisector we'll look at today is an angle bisector. So an angle bisector divides an angle into two congruent angles. Okay, and we've talked about that. We mentioned that a couple days ago. You have segment bisectors and you have angle bisectors. So an angle bisector just divides an angle into two congruent angles. You constructed those at the beginning of the year. Your theorem for your angle bisector says that if a point is on the bisector of an angle, like our F right here, BF is our angle bisector, so F is on the bisector, then it is equidistant from the sides of the angle. So this distance, FD, is going to be congruent to FE. And also remember what we talked about in terms of distance. Distance is talking about where the line hits perpendicular. Okay, like this would not be a distance. That would not be a distance. Okay, the distance is specifically talking about the line from the point to the line that hits perpendicular. Okay, but the distance from F to line BD is going to be the same as the distance from F to line BE if F is on the angle bisector. And then the converse of that theorem is that if you have a point inside of an angle and it's equidistant from each side, then that means it's on the angle bisector. So you would know that those two angles are congruent then if you see these markings. Okay, I see that right angle, so that tells me I'm looking at a distance from this point to line BE and from point F to line BD. And I can see they're the same, so that means F is on my angle bisector. Okay, so again, I'll give you a few seconds to write that down. Okay, so a few different problems. These should be really quick. Find dB. So if I want to find the distance for dB, what I can see right now is I have an angle bisector. AD is an angle bisector since those two are congruent to each other. Cut that angle in half. And I also have a distance right here since they're hitting it perpendicular. So if DC is 5, that means BD or DB will also be 5. And for the measure of angle WYZ, this angle right here, again, this is using the converse of the theorem we just looked at. Right now, all you know is that from W to line XY, that length is congruent from the distance from W to YZ. So if those are congruent, that means WY is an angle bisector. So whatever this angle measures, this angle will also measure. So if WYX is 28 degrees, that means WYZ will also be 28 degrees. Okay, and look out, they also could have asked instead, they could have given you the same information, but maybe asked, what's the measure of angle XYZ? So you would just need to make sure that you double that or look at exactly what they're asking for. And right here, I'm just gonna hold tight for a second and I'm gonna give you a little time to look at that and go ahead and write out that problem or set up your equation and try and solve through it. So I'll give you about 30 seconds or so. All right, so you should see it's on the angle bisector. So just like up here where we use the regular theorem or the angle bisector theorem, same thing. I know that QS is going to be congruent to SR since it's on the angle bisector. So 4x minus 1 equals 3x plus 2. So you get x equals 3. And then plug that back in to get QS, which would be 4 times 3, 12, minus 1, 11. And just like we had the circumcenter for where our perpendicular bisectors intersect in a triangle, we also have a certain center for where all the angle bisectors intersect. So if you were to draw all the angle bisectors for each vertex in your triangle, which right here you can see it's drawn for A, the angle bisector for B, the angle bisector for C, where they intersect that point is called the end center. The end center is going to be equidistant from the sides of the triangle. So point P, our end center right here, is going to be the same distance to AB as it is to AC, as it is to BC. So this distance right there is going to be the exact same. And that, again, that's called your end center. That's where your angle bisectors intersect, and it's equidistant from the sides of the triangle. All right, so if we want to find ST right here, if S is the end center of triangle MNP, okay, so we know an end center, that's going to be your angle bisectors. So one thing I would immediately start labeling is if I know S is the end center, then I know that all three of these lines bisect those particular vertices. So I'm going to go ahead and just label the angles with the measurements that I know they are. And I want to find length ST right here. Okay, so this is the length I'm looking for. Another thing about that end center, and I know it doesn't really look like it here, especially right here, but we're just going to trust the fact that they said it was an end center. So if they said it is, that means ST is going to be congruent to SU, which is congruent to SR. All of those three measurements should be the same. Now to solve this, if I find one of these, I find ST. So if you look, the only measurements you're given right now are SP and UP right there. But if you look, you do have a triangle, but even more specifically, because we're talking about distances and it's that right angle, we have a right triangle. So hopefully you're already thinking in your head how you can find distances in a right triangle. You have the Pythagorean theorem to help you. So your Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs, okay? So that means 8 squared plus that distance we don't know, which is SU, which would also be the same as ST. So x squared equals your hypotenuse right here, 10 squared. So you get 64 plus x squared equals 100. Give you some time to catch up. So x squared equals 36. Square root it, so x equals 6. So because SU is 6, that also means ST is going to be 6. Okay, so always be looking and see, is there any way you could find any of these other distances? Because if you can, they're going to be the exact same. And our last one, find the measure of angle SPU. So SPU is this guy right here, if S is the end center. So same kind of scenario, same measurements and everything. Right now, this is the angle we're looking for. And again, keep in mind, this angle, it's going to be congruent to this angle right here, since SP is our angle bisector. So a few different things you can look for. You've got quite a few triangles in here. Not even just these smaller ones, but you also have these bigger triangles too that can help you out. Now this triangle that I'm highlighting isn't the only one that could help us solve for this angle. There's a few different ones, but to me it's the most clear, so this is what I'm going to use. So like I've already labeled over here, I know that this angle is congruent to this angle SMR. They're both 31, so that means this entire angle would be 62 degrees. And this angle right here, since it's a linear pair with that 90 degrees, that means that right there is 90 degrees. So right now I have 62, an angle of 90, and this angle right here, that SPR, is the last angle I'm looking for. Okay, so you can use your triangle sum theorem. You know that they all add up to be 180, so 90 plus 62 is 152. 180 minus 152. Okay, so I'm just adding those together if you didn't catch that. Subtract from 180 and you get this angle right here. It's 28 degrees. I know that SPU is going to be the same measurement. So the measure of angle SPU is 28 degrees. Like I said, there's a few different ways you could have found that. I could have used like this triangle instead, that triangle NTP. There's lots that you can use, especially since you have those right angles there. All right, and last thing we'll look at is a way that this can be kind of helpful to you if you know that you're looking at the same distance to a line. So I've got a friend, Will, this is semi-true, is looking for a new place to live. He already found a new place to live. He actually did pick somewhere close, so this is accurate. But looking for a new place to live. His film studio is on Airport Boulevard right here. There are a ton of great restaurants on Manor, also true. And 35 is just nice because it can take him anywhere. So he wants equal access to each of these roads. Okay, so equal access, we'll think about it as the same distance just to the road. Not a particular point, just the road. So where should he live? So again, if we're using that idea of an end center, then we're going to be able to find the point that's going to be the same distance. So we have 3 lines. This is going to be kind of a rough sketch for airport, but let that be Airport Boulevard. This is Manor right here, and 35 right here. Okay? So there's each of our vertices, and I want to find the angle bisector of each of these. So angle bisector, again, I'm really going to eyeball it here. So we'll say that's the angle bisector of that vertex. This is about the angle bisector of that vertex, and right here. So you can see they're all intersecting right around here, which would be, let's see, that's on 34th and something. Close to 34th and Cherrywood. So there's our angle bisector, all 3 of our angle bisectors, which make this our end center. And like you guys already know, that end center, if I were to draw a line perpendicular to each of these, those distances would be the exact same. Okay? So this is our end center, equidistance from all of them, and that's how we can figure out how he can have the equal access to all the roads. All right, so that's all you guys have today. The rest of the time you can spend working on your homework 5.1. So just make sure you're keeping in mind what you're looking for, how you're setting up your equations, okay? Think about the difference between circumcenter and centers and what that means distance-wise, okay? And I will see you guys tomorrow.